We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Getting my feet out. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 104 of the Space Rocket History Podcast. And now, the first Saturn launch, SA-1. Recapping from the previous episode, the U.S. took its first step toward the moon in the spring of 1957, when the Army rocket team at Huntsville, Alabama, began study of a booster 10 times more powerful than the 150-pound thrust Jupiter. The 10-fold increase in thrust could put a weather communication satellite into orbit around the Earth or propel a space probe out of Earth's orbit. In early 1958, the Advanced Research Projects Agency, also known as ARPA, was established to coordinate Defense Department space activities. In August, ARPA formally initiated what was to become the Saturn project. The Saturn S-1 booster was too big to transport by air or land, so it was decided to build a barge and take it down the Tennessee River to the launch site. The Atlantic Missile Range was selected to launch the first Saturns. The large Booster Review Committee of the Office of Secretary of Defense, after examining the presentations of the committee, recommended the clustered Saturn booster as the quickest and surest way to attain a large space booster capability in the million-pound thrust class. The Saturn C-1 currently would consist of the clustered first-stage booster with 8 H-1 engines. The booster was designated S-1. The second stage, designated S-4, would consist of a new Douglas Corporation vehicle with 4 hydrogen-burning Centaur engines of 15 to 20,000 pounds of thrust per engine. The third stage, designated S-5, would be a modified Centaur. During the second half of 1960, there were several successful static test firings of the Saturn C-1 first stage, culminating in December with an all-8 engine firing for 60 seconds. During 1961, configurations seemed to change month by month. In January, the C-1 vehicle changed from a 3-stage to a 2-stage booster, eliminating the S-5 upper stage to leave only S-1 and S-4 stages. But S-5 development continued during February. By May, the C-1 had become a possible 3-stage vehicle again, including Block 1 and Block 2 interim versions. In February, the C-2 was ticketed as a 3-stage vehicle for Earth escape missions, featuring an S-2 second stage. In May, there was talk of a need for an even more powerful vehicle for circumlunar missions. In June, the C-2 was dropped in favor of a C-3, although Nova would continue. Later in the year, there were plans for a C-4 along with a solid booster C-1. By the end of the year, there was also the C-5. One result of this was the decline of Dinosaur, whose position as a NASA payload essentially evaporated after the C-2 cancellation in June. In case you are wondering what the Dinosaur was, it was a single-pilot manned reusable space plane. It was canceled in December of 1963. The rise and fall of vehicle configurations reflected the rapidly shifting concepts of mission profiles, payloads, schedules, and money. The fluctuating pattern of Saturn configurations and numbers created confusion even among those in government who were close to the program. Some critics were concerned that future development of Saturn was a dead-end road, and if the critics were referring to the Saturn S-1 first stage with a total thrust of 1.5 million pounds, then they were right. The S-1 had reached maximum development, since the propulsion came from the most advanced engines available from the ballistic missile program. But the critics did not allow for the advanced Saturns of much improved performance using the new Saturn engines such as the F-1 and the J-2 that used a liquid hydrogen propulsion system. Both of these engines would be crucial for advanced configurations involving more ambitious missions. The C-3 version, for example, boasted 2 F-1 engines in the first stage, double the thrust of the existing Saturn C-1 first stage, 4 J-2 engines in the second stage, and a pair of J-2s in the third stage. During a high-level NASA conference in late July 1961, Milton Rosen emphasized that the U.S. was still in competition in the race for a manned lunar landing, only because we initiated J-2 and F-1 at a relatively early date. If the United States intended to maintain a competitive position, Rosen warned, NASA had to capitalize on the use of these propulsion systems, both of which were still under development. This brings us to the first Saturn launch, SA-1. We will begin with the new checkout procedure. Just as Launch Complex 34 dwarfed its predecessors, Saturn checkout represented a new magnitude in launch operations. The Saturn C-1 stood 3 times higher, required 6 times more fuel, and produced 10 times more thrust than the Jupiter. Its size, moreover, was only a part of the challenge to the Launch Operations Directorate at Cape Canaveral. The cost and complexity had also increased markedly. Because of the cost, eventually $775 million for the Saturn I's program research and development alone, there would be fewer test flights. This meant the engineers at Marshall Space Flight Center had to have more test data per flight. Whereas 2 telemetry links sending 116 measurements had been adequate for redstone testing, the first Saturn booster employed 8 telemetry links to report 505 measurements. The rocket's overall complexity necessitated a longer checkout. Saturn C-1 launch preparations averaged 9 weeks, almost 3 times longer than for a Jupiter missile. Ultimately, the new procedures were to work a major change in the human role on the launch pad. Until the Saturn, the DeBoost team had been on a first-name basis with the rockets. Launch Operations Directive members who were not crawling around inside the Jupiter worked within a few yards of the pad. The Saturn brought little change initially. Checkout for the first Saturn C-1 remained largely a manual operation. In the blockhouse, a console operator with a test manual threw a switch connected to a rocket component and checked the results on a meter or strip chart. Automation on the first Saturn booster was rudimentary, limited to relay logic during the last minutes of countdown. It increased as the Saturn grew more complicated. The addition of a live second stage to the Saturn C-1 and the appearance of the much larger Saturn V dictated greater reliance on machines and computers. By the mid-1960s, the Saturn checkout was well on the way to automation. NASA had firmed up the Saturn C-1 program in late 1959 by adopting the Silverstein Committee's proposals. Marshall Space Flight Center would start with the clustered booster S-1 and a dummy upper stage. A second block of missions would add a hydrogen-fueled second stage, and a third block would add a third stage to the stack. The program office listed the SA-10 launch set for April 1964 as the Saturn C-1's debut as an operational ready vehicle. Plans beyond the 10-vehicle research and development schedule were indefinite. A 1960 NASA long-range program called for 50 Saturn C-1 and C-2 launches between 1965 and 1970. 20 of these flights would launch Apollo spacecraft reentry tests, Earth orbital missions, and circumlunar flights. These plans were altered in January of 1961 when Wernher von Braun proposed to eliminate the third stage. A two-stage Saturn C-1 would meet the needs of the early Apollo missions. Following NASA headquarters approval of von Braun's recommendation, the Saturn office in Huntsville rearranged the 10-vehicle R&D program. Block 1 of the program, beginning that fall, would consist of 4 S-1 stage tests from Launch Complex 34. That would be mission numbers SA-1 through SA-4. Block 2, the next 6 launches, SA-5 through SA-10, would add the second stage from the Launch Complex 37 launch pad and from an upgraded Launch Complex 34. The Saturn C-1 test flights were to prove the design of the launch vehicle. The Block 1 launches in particular would test the 8-engine propulsion system, the clustered tank structure, the first stage control system's ability to cope with sloshing and non-rigid body dynamics, and the capability of the vehicle and the launch facility. During the Block 1 series, Marshall engineers proposed a systematic buildup of tests to prepare the way for two-stage flights. Broadly stated, Launch Operations Directorate responsibilities were fourfold. First, assuring that transportation had not affected vehicle components. 2. Mating stages and grounding equipment to verify the compatibility of the different stages. 3. Launching the rocket. And 4. Analyzing the performance of all vehicle systems immediately after launch to detect flight failures. Although the mission was referred to as Launch Vehicle Test and Checkout, less than half of the Launch Operations Directorate's scheduled activities involved test performance. The balance of the total launch preparation effort included activities more properly described as assembly, installation, preparation for test, and evaluation of records. Now let's move on to the launch readiness and checkout personnel. The overall leader, Kurt DeBoos, kept a close eye on SA-1 operations, but other problems occupied his time as well, such as a new launch facility for Saturn V, Centaur facility development, and Mercury Redstone, Pershing, and Ranger launches. Because of these duties, DeBoos did not deal with the details of the SA-1 checkout. That burden fell on his operations office chiefs, their deputies, and the veteran test engineers. Dr. Hans Grün headed the Electrical Engineering Guidance and Control Office. He was a native of Braunschweig, Germany. He had earned his engineering degree at the Technical University in his hometown. Grün had joined the Peenemünde operation in 1943 and immigrated to Fort Bliss after the war. Since 1951, he had served as the electrical network's chief for the launch team. Small in stature and unassuming, Grün enjoyed great respect from his associates. Grün's deputy, Robert Moser, had joined the von Braun team as an Army enlisted man in 1953. 3 years out of Vanderbilt University. He had reverted to civilian status in 1955, but stayed on in Huntsville as Grün's right-hand man. Moser's launch countdowns resembled an orchestral performance and earned him high praise as test conductor for Explorer 1 and Alan Shepard's Mercury Redstone flight. Gruhn's office supervised the performance of all equipment affecting rocket guidance and control. This required a wire-by-wire knowledge of the electrical system, both on board of the vehicle and at the launch site. Gruhn's men also evaluated pre-flight telemetry records relating to guidance, stabilization, control, and electrical networks of the vehicle. Albert Zieler's Mechanical, Structural, and Propulsion Office handled missile receipt and transfer, stage erection, and assembly. The team tested pressures, located leaks, and made necessary replacement repairs or modifications. One of the branch's sections was responsible for fueling the rocket, another for the firing. After the launch, the branch evaluated flight data to check on mechanical functions and make corrections for future flights. The Australian-born Zieler had served at Peenemünde throughout World War II, testing and launching V-2s. Following duty at White Sands, he had moved to Huntsville and worked for the Missile Firing Laboratory. Robert Gorman, deputy in the mechanical office, had begun his engineering career in NACA's wind tunnels at Langley Field. He was known for listening to his subordinates' ideas. His calm manner balanced Zieler's excitable nature, and the two provided the office with effective leadership. Quiet and intense, Carl Sandler, chief of Measuring and Tracking Office, seemed aloof to strangers, but to colleagues showed a warmth that sparked loyalty. He was trained in Vienna and reflected the traditions of the old Habsburg capital in his manner and attitude. At Peenemünde, Sandler had tracked the V-2s fired northward along the Baltic experimental range. He too had worked at White Sands before moving to Huntsville in 1950. His deputy, Grady Williams, had graduated from Auburn in 1949 and joined the von Braun team 3 years later. Associates considered him one of the friendliest members of the team. Like Sandler, Williams had a penchant for order. The two gave the Measuring and Tracking Office a reputation for being immaculate. During checkout, Sandler's systems engineer tested and calibrated the Saturn's measurement instruments, pressure gauges, thermometers, accelerometers, and the telemetry that relayed the measurements back to Earth. At launch, his office collected the flight data from ground radars that tracked the flight for deviations in direction and range, which would reveal problems in the guidance and propulsion systems. Along with the other offices, Sandler's group prepared designs and established criteria for launch facilities. The unit's work brought frequent contact with other agencies investigating telemetry, high-frequency signals, and the measuring and tracking of launch vehicle flights. The work of the 3 Launch Operations Directorate offices involved close liaison with other Marshall divisions. Thus, Hans Gruhn and his engineers spent more than half of 1960 and 61 in Huntsville with the Marshall Guidance and Control Division. In turn, a dozen guidance and control engineers took part in the SA-1 checkout at the Cape. The launch team still considered itself an extension of Marshall. As one veteran recalled, in the 1950s we looked at equipment when it came down here as not trusting a single thing in it. We were going to check everything from the one end to the other. Consequently, Launch Operations Directorate checkout was precise and exhaustive, a laboratory-type check on the pad. Basic operation procedures were established and followed closely. The technical checkout of the various Saturn systems fell to Launch Operations Directive's test engineers. DeBoost considered these engineers the backbone of the Launch Operations Directive test activities. They carried full responsibility for preparing a launch vehicle to the point of launch readiness and merited equal status with engineers in design, development, and assembly operation. While an error made in design or development phase could be detected by a test engineer, a mistake made by a Launch Operations Directorate systems engineer would inevitably lead to mission failure. Although limited manpower ruled out a 2-day shift operation at the Cape, when problems arose, the launch team resorted to overtime. The working day during the SA-1 checkout period varied from 8 to 16 hours. Now I want to talk a little bit about the journey of SA-1 as it went from Huntsville to the Cape. 2 years earlier, Marshall Flight Center officials had decided to transport the Saturn booster from Huntsville to Cape Canaveral by water. Of course, before they put the real Saturn booster on the barge, they needed to run a test. So, in April 1961, Test Division personnel loaded a water ballast tank, the approximate size and weight of the booster, and a dummy upper stage aboard the barge. The barge resembled a Quonset hut on a raft. It was propelled by a tugboat. The barge made the first leg of its trial trip in 5 days, descending the Tennessee, Ohio, and Mississippi rivers to New Orleans. There, a seagoing tug replaced the river tug. The paddlemen crossed the Gulf of Mexico to the Florida Keys, sailed through the straits and up the Atlantic coast via the Intercoastal Waterway. The test went well and served its purpose, proving that both the paddlemen and the Cape's secondary roadways could carry the load of Saturn. The paddleman was undergoing modifications back at Huntsville in early June when the lock at Wheeler Dam, Tennessee, collapsed. This stranded the barge upriver. So, the Test Division and Launch Operations Directorate personnel moved quickly to secure a reserve barge from the Navy's mothballed fleet at Green Cove Springs, Florida. Although there was not enough time to construct a cover for the second barge, the Avondale shipyards at Harvey, Louisiana, made emergency modifications. Concurrently, the Tennessee Valley Authority enlisted the Corps of Engineers to build a bypass road and dock at Wheeler Dam. NASA named the barge Compromise in hopes it would prove a workable one. The booster was ready for shipment in early August, following static firing and 2 months further testing at Redstone Arsenal. To protect the booster during its voyage, the Test Division installed humidity and pressure regulating equipment within the liquid oxygen and RP-1 kerosene systems. Protective covers were placed on each end of the booster, as well as on the dummy upper stage and payload. Next, support cradles, connecting trusses, and assembly rings were added to the assembled booster, and it was placed onto 2 axle and wheel units. Then an M26 Army tank retriever towed the load to Redstone's dock. The portage at Wheeler Dam, the reloading on the Compromise, and the journey to New Orleans went smoothly. Out in the Gulf of Mexico, however, the 10-man crew had rough sailing. Test Director Carl Heimberg attributed the handling problems to the Compromise's insufficient ballast. Negotiating the Intercoastal Waterway proved even more difficult, and the Compromise went aground 4 times. Heimberg blamed this on unreliable channel depths due to the shifting of the loose sandy bottom. Crosswinds were an additional hazard. Besides threatening to blow the barge around, the wind caused several near accidents at bridges. In fact, the Compromise collided with a bridge on the return trip, causing minor damage. Despite Heimberg's frustrations, the SA-1 arrived unscathed at the Cape's Saturn dock on August 15th. Unloading the booster was relatively easy in the almost tideless Banana River. Henry Crook's vehicle handling unit towed the S-1 transporter across the Cape at a speed of 6.5 kilometers per hour. Although the operation required little physical exertion, the 10-man team perspired freely on the treeless Cape. At Pad 34, ocean breezes made the heat and glare more tolerable. The booster, or S-1 stage, was erected on Sunday, August 20th. Crunk's unit had practiced maneuvering a dummy tank on the pad, but this was the first mating of a real booster to the launch pedestal. With the service structure in place over the pedestal, an M26 driver positioned the transporter parallel to the service structure base. The crew connected crane hooks to pickup points on the booster. First, a 60-ton hook to the forward sling, and next a 40-ton hook to the thrust frame sling. The crane operator raised the S-1 stage vertically, brought it into the service structure, and lowered it onto 4 pre-leveled support arms. Removal of the transportation assembly rings proved to be the most time-consuming aspect of a thankfully uneventful operation. Early the following week, Crunk's unit hauled the dummy stages and the payload from Hangar D, where they had undergone inspection. Then the handling unit mated the dummy stages and the nose cone on August 23rd. On August 25th, cables and cable mast were installed, the 4 retractable support arms positioned, and network power applied. Concurrently, the fabrication division installed exhaust duct brackets, access doors, and the radio frequency shield. At last, Saturn SA-1, with a live S-1 first stage and dummy upper stages, was on the pad and ready for final checkout. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.